Hello everyone. So we already have started sensor physics part, and in the last lecture we have covered thermal sensors, how thermal sensors or what are the different considerations associated with thermal sensors, how one should consider different parameters related to thermal sensors while fabricating a temperature sensor or a thermal sensor. And we have seen that, in a nutshell, if I say, then if there is an object and if there is a temperature sensor connected or attached to that object, then the coupling between the temperature sensor and the object, the thermal coupling should be very high, and the thermal coupling between the sensor and the environment should be low. So it should be poorly coupled thermally, and in this situation you will get the best performance from your temperature sensor. So today we will start a new type of sensors, that is chemical sensors. And chemical sensors, from the name itself it is very clear that these sensors are used to detect different chemicals. So obviously they are based on different chemical reactions. I won't say it's chemical reaction. So we actually classify chemical sensor based on the reaction. If the sensor is physically reactive, then we call it physically reactive sensor. If it is chemically reactive, then we call it chemically reactive sensor. Now, if we take an example of physically reactive sensor, so the reaction should change the mechanical property of the active material. So if you have a sensor, and we know what is an active material in a sensor, so if the mechanical property of that active material changes due to certain sort of reaction, then we call it physically reactive chemical sensor. What are those mechanical properties could be? This could be the stiffness, softness, stretchability, flexibility, and so on and so forth, right? If some of these mechanical parameters, or there are many other mechanical parameters as well, say elastic modulus, this and that. So if these are changing, then we call it physically reactive system. And on the other hand, if the reaction changes electrical property of an active material, so electrical properties are, for example, resistance, capacitance, inductance, and so on and so forth. So if the reaction, whatever is happening, is changing the electrical property of the active material of the sensor, then we call it chemically reactive chemical sensors. Apart from that, we also can categorize chemical sensor as direct sensor and indirect sensor. So direct sensors are to some extent simpler in their configuration. Indirect sensor or indirect sensors are to some extent complex comparatively. So if we compare, you'll find that indirect sensors are a bit complex. So let us also see what do direct and indirect sensor mean. So here a schematic is shown for direct device or direct sensing. If you have a sensor, in this case it's chemical sensor, if that chemical sensor is giving you an electrical signal due to the reaction directly, then we call it a direct sensor. There is no indirect process involved. Some material, say active material here is A, it is reacting with B, and then as an output you are getting an electrical signal. So we call it direct sensing. On the other hand, if the reaction in the sensor is giving you a different sort of output, for example, say it can be an optical output. We probably have already discussed an indirect sensing concept I'm again discussing over here because it will help us to understand the concept of indirect device. So for example, say if you have a material A, this is analyte, okay, and this particular material is reacting with the sensor or sensor's active material B, and due to that reaction the color of the sensor is changing. So you have a sensor strip, this strip is reacting with the analyte and the color of that strip is getting changed. So for example, again we may take, due to the reaction the color of the sensor is changing from dark blue to a lighter shade, so light blue. Okay. Now if the concentration of this analyte is high, we get a lighter shade. If the concentration is less, we get a darker shade. So initially say it's a dark blue colored sensor strip. The moment you put analyte on that sensor, the color changes to lighter shades. If the concentration of A is say 10 unit, it becomes bit lighter blue. If it's 100 unit, then it becomes even lighter, right? Now one can take this sensor and put into a sensing system where you have a light source and say a detector, optical detector or light detector. Now the light source is used to send optical signal on the sensor, and you have a sensor, just you have placed the sensor in a way that the light that is coming out of the light source is getting reflected and falling on the light detector, right? This is the reflectance, or I would say the model which is taking advantage of the reflection. You can also use in transmission mode. So in that case you put the light detector, on the other side of the sensor, then the light will fall on the sensor and a portion of that light will get transmitted and will fall on the detector. Both ways it's possible. I'm giving you an example. Okay. Now if the color of this strip is changing due to the concentration or reaction, due to the reaction between the active material and the analyte, then that color change will also influence the reflected optical signal or transmitted optical signal. Now if you detect the reflected optical signal using a photodetector or light detector, you will get certain sort of output for different colors. If the concentration is high, you will get the output, because the output from the light detector is electrical signal. So there is a transducer here. So the transducer is placed after the sensor, electrical transducer I am talking about, because ultimately we need electrical signal in order to process that in a electronic system. I mean, someone may say that the sensor here, this optical sensor here, which is a colorimetric sensor, based on the, it is showing the result based on the change in color, which is visually also visible. You can see that. You don't need a system for that purpose, but if you need a higher resolution, shade by shade changes and something of that sort, or the color change is not that prominent, in that case it's better that you take advantage or you take help of an electronic system. That is what you can do. In fact, in this case also you can take help of an electronic system, because then it will be a kind of a standard analysis. Otherwise, somebody may detect the change in color. If there is a small change in color, somebody may not detect, because it depends on their capability, visual capability, and it varies from person to person, right? So in this case, this example shows an indirect sensing concept. You have a sensing in here, then you have developed a sensor, a system for the electrical transduction, and then you receive the electronic signal from that transducer. In this case it's light detector, and based on the change in concentration, you will see that the electronic signal also is changing. either increasing or decreasing based on whether the reflected light intensity is increasing or decreasing, or transmitted light intensity is increasing or decreasing. So here I have explained two modes. One is reflected light mode, another one is transmitted light mode, right? So this is an indirect sensing concept. So that is how we can also divide direct sensing and indirect sensing. We can categorize chemical sensors as direct chemical sensor or indirect chemical sensor. Now let us take an example, which is a very basic example of a gas sensor. Okay, and usually for a gas sensing application, people use metal oxides. So in this case, we will take an example of a metal oxide sensor, metal oxide gas sensor to be specific. So the metal oxide you may choose in this case is say SnO2, that is tin oxide, and the metal oxide's electrical property changes in presence of reducible gases. That reducible gas could be methyl mercaptan. This is a gas that is reduces, or it has a reducing property. Okay. Now the concept behind this sensing is this gas will reduce the oxide present in the active material, or here the oxide itself is the active material, right? Similar gas sensing application or gas sensing demonstration was reported in early 1960s. So it's again a very old concept if you consider today's time. But even today you'll find that there are multiple even commercial gas sensors which are based on metal oxide. So the concept is even today it's not obsolete. People are taking a similar concept in order to make gas sensors. So here I have shown a scheme that will help you to understand how it works. So if you have a metal oxide, in this case I am just showing the active material part of the sensor, then the metal oxide usually has a surface potential associated with it because of the adsorption of oxygen, not absorption. Absorption is something different. Maybe in the next slide we will discuss what is the difference between absorption and adsorption. So because of adsorbed oxygen, you'll find there is a surface potential associated with the metal oxide film. Now this surface potential inhibit the flow of electron. It restricts the flow of electron because there is a potential present. So it restricts the flow of electron in that material. Now if you have a reducible gas, the example is shown over here, methyl mercaptan, it will decrease the surface potential because it will reduce some of these adsorbed oxygen, and that surface potential decrease in turn will increase the flow of electron, because previously the presence of that surface potential was restricting the flow of electron in that material. Now because you have a reducible gas, it decreases the surface potential, and that's why there is an increase in the flow of electron. So definitely you will get large number of current because electron flow has increased, carrier flow has increased, right? So if your concentration of the gas is higher, you will find high number of electron flow, and hence the concentration of the gas can be directly related to, or you can correlate the current with the concentration of electron, and that is how you can detect the gas under consideration. In this type of setup, usually heat sources are used, micro heaters and stuffs like that, so that the adsorbed oxygen, they gets dissolved, so that you can reuse the sensor. Until and unless you dissolve that oxygen, you cannot reuse that sensor. So for the reusable purpose, people also use micro heaters with this type of sensors. Apart from that, some of the reactions are more suitable in high temperature. So this reducing reactions at times are more preferable or kind of more prominent in high temperature zone. So, if high temperature range. So, if you apply high temperature, these reactions are more suitable. That is why also people put micro heaters in order to keep the surface of this material, active material, heated, right. So, this is a simple concept which one may use in order to detect gas. Now, as I have said that in this case one has to remember that the concept or the oxygen on that material is actually adsorbed, not absorbed. So, what is the difference between these two? So, absorption is usually a bulk phenomena. So, when there are molecules, if that molecules are going into the material, inside the material, then we call it absorption. So, it's not that much dependent on temperature. The dependency of temperature is comparatively less, or at times it's, in many cases it's not at all dependent, and it's an endothermic process. However, on the other side, adsorption is a surface phenomena. So, all these molecules will stay on the surface of that material, they will not go into the material, right. Adsorption is favored by usually low temperature. If you increase the temperature, the adsorption will reduce, and it's a exothermic process. Okay. So, this is the basic difference between adsorption and absorption. So, one has to be very careful about when they are describing the concept, because both these phenomena are very different in principle. Now, the film resistance Rs and the concentration of the reducible gas C both can be related with this equation. So, they are related with this equation, according to this equation. So, your Rs is equal to A into C to the power minus alpha. This is an empirical equation. Empirical equation means after a lot of experimentation and studies, they figured out that the relation is of this sort, where A is a constant which is specific to gas and alpha is characteristic slope of Rs curve. So, this slope you may get from the calibration graph. So, this is the typical equation associated with the gas sensing of this sort. Okay. Apart from that, you also will find that there are different electronic device based chemical sensing. So, here scheme or schematic is shown which shows a chemical FET, field effect transistor. So, field effect transistors have actually it has 4 electrodes: source, drain, gate. So, it's actually a MOSFET, it's a MOSFET structure, and you already have probably studied about FET and MOSFET in your electronic device courses. Even if you have not studied, I am just giving you an idea how it works. So, if you have a source, if you have a drain and gate, and then there is a bulk electrode which usually we ground. So, here we are not considering the bulk electrode. So, just consider you have a source electrode, drain electrode and a gate electrode. Now, if you put a potential between source and drain, then based on the gate potential, the current between source and drain will change. Usually, you need a minimum gate potential in order to create the channel, that is carriers here. If there is no channel, there will be no current between source and drain. So, if you put a minimum amount of gate voltage, a channel will be formed, and then if there is a potential between source and drain, you will see that the current is flowing from the positive terminal to the negative terminal. Okay. Now, in this setup, one may use a gas selective membrane and then a hydrogel, the way it is shown, on top of the gate electrode. And because this membrane is gas selective, this will only allow, say, a selective gas or a specific gas to pass through it. So, once the gas passes through it, it changes the potential of the gate. I already have shown you if there is certain sort of surface potential associated with it, Now the gas will come and will change the potential of gate, and that gate potential will in turn change the current, source drain current. So the concentration, again, say if this is gas A, which is the only gas allowed through that membrane, so that gas will go through that membrane and will change the potential of gate. If the concentration of A is high, it will change the potential of gate to one higher extent. So the current will also change accordingly, right? So in this case, you'll find that the concentration of A can be calibrated with the source drain current. So this is a typical structure of a chemical FET, right? So here, say if you take an example of hydrogen, if you create a gate electrode with palladium and nickel, and the hydrogel if you take as a silver chloride, and then if you take a gas hydrogen selective membrane, in that case the hydrogen will react with palladium nickel. Usually, palladium nickel, this composite adsorbs hydrogen, and that may change the electrode potential, that in turn will change the current between source and drain. And then you will find that the concentration of hydrogen can be related to the concentration of hydrogen. If you change this gas selective membrane with an ion selective membrane, then this particular setup can also detect ions, because ions also will change the electrical property of the gate electrode or the potential of the gate electrode. So just by changing the gas selective membrane with an ion selective membrane, you can also make it a ion detector in a certain solution, or the gate itself can be replaced or coated with chemical selective electrolyte. In that case, it can detect a specific chemical. Okay, so based on that, if your membrane is ion penetrable, this is termed as MEMFET. If your membrane is ion impenetrable, this can be termed as SURFET. If the gate coating is enzyme membrane, then we call it NFET. If the gate coating is ion selective, we call it ISFET. Now ISFET is a device which are used for various of chemical sensing applications. Okay, and then there are different other structures also. This is a simple MOSFET structure. Then people also use extended gate, where they have a device over here, MOSFET device over here, then they have gate electrodes. They extend the gate, and then at some or away from that device, they do these chemical reactions, because sometimes the chemicals may also influence the device properties, because you are putting or exposing the device, almost you are exposing the device to that chemical. So the chemical reactions may also change the properties of the device, and in that case it becomes very difficult to identify whether the change in current is due to the change in gate potential or there is some other reactions happening. So what people do in that case, they extend the gate and then do the reaction away from the device so that the device is protected. So there are different other techniques also associated with a similar concept, but these are a few that you may find in literature very often. Okay, so three take-home messages from today's lecture is chemical sensors are of various types, like other sensors as well. We have seen this can be physically reactive, this can be chemically reactive. Then we have direct sensing and indirect sensing concept. Indirect sensing is possible in chemical detection. So one example we have seen that if there is certain sort of chemical sensor which shows a change in color, the same can be integrated with a system, optical system, through which you can detect the change in color in terms of electrical output. Then electronic device based chemical sensors can be fabricated. So one example we have seen, which is based on a MOSFET structure. So not only MOSFET, you also can make a micro electromechanical system based chemical sensor. You also can make say PN junction based chemical sensor. So the idea is the electrical property should be a function of that chemical reaction, so that you can detect the concentration of an analyte precisely using that device. So in the upcoming discussion, we will see some more chemical sensing concepts. Till then, thank you.